Hello everyone, my name is Sasha and welcome to the third video in the curve sketching series. In previous videos, we covered the basic idea of curve sketching, we talked about sign diagrams, and we covered these first 4 steps of curve sketching. So if you're a little bit confused on that, I would recommend going to check the previous videos. However, we are going to be talking about the second derivative today, and also check our work with Desmos and talk about some tips and tricks for handling more challenging problems. So the first thing that we are going to do is take the second derivative, and this is going to be very similar to taking the first derivative, where we're basically just going to be taking the derivative of our first derivative. And again, we can apply the power rule, which is listed right here, to be able to solve these problems, and we get 36x minus 8. And just like last time, we want to find the zeros of this function because then we can create a sign diagram which will tell us how the graph is behaving at different points in terms of its concavity, which again means if the graph is bowl-shaped up or bowl-shaped down. So we can go ahead and take the zeros of this function by putting this against 0. Oh, hang on, 36x minus 8 equals 0, and here again it's just a little simple two-step equation. Add 8 on both sides, and then we get 36x equals 8. Divide by 36, and we get x equals 8 over 36, or 2 over 9 when you simplify the fraction. Now that we have an idea of this sign diagram and the 0 of our function, let me flip my notebook, and the 0 of this function, we can go ahead and plug this into our sign diagram. So we have x on top, we're taking the sign diagram of the function f double dashed of x. I find it very helpful to indicate which graph or which function we are dealing with in the sign diagram. And our important point as we move from negative infinity to positive infinity is 2 over 9, that being our x-intercept, the point at which the y values shift from being positive to negative or negative to positive. And once again, we can kind of take a look at a value before and a value after. So we can pick 0 for a value in the more negative direction from 2 over 9, and we can see that we would get a negative number as this first term would cancel out, leaving behind just a negative number. So before, we have a negative number. Yes. And then after, we can pick a number like 1. We have 36 times 1 minus 8. That is going to be a positive number. So we can see that here we have bowl shape down, bowl shape up, meaning that this right here is our inflection point in our function. And if the concept of concavity is a little bit confusing to you, I totally get it. It kind of just takes practice and like working with different problems and seeing it. I personally was really confused about the difference between slope and concavity for a very long time, but doing these kinds of curve sketching problems have kind of like shown me the difference between them. As you can see, the slope on this graph, or on this little bowl shape, is changing, and it starts out being positive and then it ends up being negative. However, the concavity of the graph, the fact that it is bowl shaped down, is always consistent over the entire thing. So like last time, now that we know the x value corresponding to f double dashed of x, we can go ahead and plug that back into our original problem, our f of x function, to get a good sense of where the y value is, so we can go ahead and plot it on our graph. And I will go ahead and save you the algebra. It is 2.869. And like before, we can go ahead and plot that on our graph. It's about 1/4, and it's like there in the middle. So that kind of checks out. Here's our inflection point, here's our max, here's our min, so it'll go like that. And the end behavior is positive, so it'll go upwards into infinity, and from here it'll go downwards into infinity. So let me see if I can go ahead and draw it, but I'm using a trackpad, so it's going to be very bad. Well, that wasn't too bad. Okay, but there's a rough sense, a sketch, if you will, of how the function f of x equals 6x to the third power minus 4x squared plus 3 would look like. And we can go ahead and check our work in Desmos. Here's our very own curve sketching example. And as you can see, we have a max at 0, 3, a minimum at 4/9, or corresponding to decimal form, 0.4444, 2.737. We said 0.736, but due to rounding errors, it's basically the same thing. And we can see that as over here, there's bowl shape down, over here it's bowl shape up, and in the middle, it kind of switches about here to the value that we said was just about corresponding. We said 0.869. So it looks like we did a great job of doing that curve sketching, and so I hope that was helpful for you. Maybe you were able to follow along with your own example that you were working on, but Desmos is also a great tool if you have it available to you when working on these kinds of problems in order to be able to check your work. Now I want to kind of show you some tricks for more difficult problems. These first two deal with what happens when there is something in your denominator. And this first expression you can see looks quite complicated, but it actually is only just a linear function, which is because you can factor the numerator to find cancellations. So x squared minus 9 factors out to be x minus 3 times x plus 3, and the x plus 3 on the top and bottom cancel out, leaving behind just x minus 3. As you can see, all of these are the exact same function. The second trick, if things don't cancel out very easily, you're going to get something called an oblique asymptote, which is neither vertical or horizontal, but instead slanted like a linear function. And you'll see it's like that there. And you can find this by doing polynomial long division, which is not something I'm going to be covering in this video, but there are plenty of fantastic resources online for you to check out in order to be able to conquer this scary looking curve sketching conundrum. My next tip and trick, and this is one that we actually used in our video, or in our example, was to use factoring to our advantage. So here we have a quadratic function, and here we have the exact same quadratic function. However, we have retracted an x out of it in order to create two different factors that we can solve for the roots more simply. And as you can see, the roots correspond to what we would get if we were to solve this thing, and that is negative 1.5 and 0. It is possible to find the rational function, or to find the, it is possible to find the roots using this. However, the quadratic formula is kind of a pain, and I obviously love to avoid it if I possibly can. The second tip, or the fourth tip and trick, and this one I think is very helpful, is that you only have to evaluate the numerator when looking for x-intercepts. As you can see, these two functions here have very, very different denominators, but the numerator is still the same. And lo and behold, even though they are crazy functions and they look super different, they have the exact same x-intercept. And this is helpful for if your denominator is very confusing, and would make finding x-intercepts difficult, but your numerator would be kind of simple to find x-intercepts. This is a great tip and trick. And lastly, in the same vein, you only have to evaluate the denominator when looking for vertical intercepts, or vertical asymptotes. So here are two functions. You can see that their numerators are extremely different. Their denominators, however, are exactly the same, being x plus 2. And you can see that when we go ahead and look at that, they both have asymptotes at x minus 2. So here are a couple tips and tricks for you to use in your own curve sketching questions when you encounter things more difficult than our very own curve sketching example. I hope that these series of videos were helpful for you, and I wish you luck in all of your curve sketching adventures. Bye!